Well, here's the question that I asked at the end of the first part of this lecture. Now, we know a relationship between the electrical force and the distance between the charges. We know that the electrical force is proportional to 1 over the square of the distance. And so that means E can't be right. We know how to do this. In particular, note that we don't need to know the force as a number. We just need to know by what factor the force has changed. Next, note that we know that the electrical force decreases as you increase the distance, but we've decreased the distance, and so the force must be larger, and so it can't be A or B. Those are both smaller than our original. Now just look at that proportionality. It's 1 over r squared. We've multiplied r by a factor of 1/3, and so we have to multiply f by a factor of 1 over 3 squared, or 9. We get 9 times the original force, and what I've just done is called proportional reasoning. If you got to this answer, but you had to do it by making up numbers and plugging them into a relationship, then you're working too hard. You need to learn to do proportional reasoning, which will let you do this sort of thing in 3 seconds flat. I had hoped that there were lots of good videos on proportional reasoning on YouTube, but as it happens, most of them aren't very good. I will post a link below to one that I think is pretty good. Knowing the proportionalities is all we need to know to be able to write down the relationship between the electric force and these quantities that it must depend on. And so here is the relationship. And if you just look at the structure of it, you can see that the electric force is proportional to both Q1 and Q2, and it's proportional to 1 over the distance squared. And like any proportionality, this must have a proportionality constant in front. You wouldn't expect that if you multiply together 2 charges and then divide by a length squared, you would get an answer that has correct units to be a force. And so there must be some proportionality constant which gives us an answer in a unit of force. And the value of that constant will depend on the units we're using for charge, distance, and force. Notice that I have not written a vector symbol in this equation. Now, of course, the electrical force, like any force, is a vector, but this equation is not giving us the electric force vector. It's only giving us the magnitude of the electric force. And by definition, a magnitude must be positive. That's why these two Q's, Q1 and Q2, are in absolute values, because of course one or both of those charges could be negative. And so we need these absolute values here to ensure that we get a magnitude that is positive as it should be. Keeping with the theme of what is a vector and what isn't, note that r12 in the denominator here is the distance between charges Q1 and Q2, and like any distance, it is by definition a scalar. Now, that distance is the magnitude of a displacement vector pointing from Q1 to Q2, and of course, if you set up axes, you can define the positions of charge 1 and charge 2, and then that displacement vector is just going to be r2 minus r1. And so this distance is the magnitude of that vector subtraction. However, I'll point out that most of the time going through all the vector algebra to do it that way is too much work. You might as well just calculate it as a distance like you would find any other distance. Also notice that if the force that 1 exerts on 2 is given by the relationship I wrote above, then below we can write the force that 2 exerts on 1. It's just kq2 q1 over r21 squared. Well, r21 is just the distance between q2 and q1, and that's the same as the distance between 1 and 2, by definition. And reversing the order of q1 and q2 in the numerator won't change the answer. And so clearly this is saying that the force that 2 exerts on 1 is equal in magnitude to the force that 1 exerts on 2. Phew! Good thing we came up with that, because Newton's law, Newton's third law, insists that that must be true. If we had come up with any other answer, we would have to conclude that our force law for electrical forces was wrong. However, luckily it does work that way, or one way of seeing it is that Coulomb's law has Newton's third law built into it. Well, now it's time to talk about units. And since we've actually been defining charge in terms of electrical forces, you could say that what we do is measure electrical forces, and then via the value of the proportionality constant k, we define our units of charge. And in principle, you could do it that way. In practice, that's not how we define our units of charge, but we won't really be able to understand how we define units of charge until much later in the course. So for now, you might as well think of it as simply related to sizes of electrical forces. The SI unit of charge is the Coulomb, and we'll see in a moment how to think about what a Coulomb is, but one way of thinking about it is to think of it in terms of the fundamental charge unit. The fundamental charge unit E, which is the charge on a proton, is 1.6 times 10 to the negative 19 coulombs. Or in other words, it takes around about 5 times 10 to the 18 protons to give you 1 coulomb of charge. Let's just quickly figure out the units of the constant k. So if we're working in SI units, we know that each of these charges will be in coulombs, this distance will be in meters, and the force will be in newtons. And so what we have is that newtons must equal k, whatever its units are, coulombs squared over meters squared. And so there we have it. K must be in Newton meters squared per coulomb squared. Now that we know what the units of the proportionality constant k must be, we can write down the value, and you can think of this as something we just measure. And it's 8.99 times 10 to the 9 Newton meters squared per coulomb squared, or about 9 times 10 to the 9 Newton meters squared per coulomb squared. K, the constant, is often called Coulomb's constant, but it goes by a variety of other names. It's also called the electrostatic constant or the Coulomb's law constant. I'll tend to just call it K. We can get a bit of an idea of what a coulomb is just by thinking about what would happen if we had a 1 coulomb charge and another 1 coulomb charge separated by 1 meter. What would be the size of the forces that they exert on each other? Well, that's pretty easy because it's going to be 9 times 10 to the 9 times 1 coulomb squared, all divided by 1 meter squared. And so all the meters are gone and all the coulombs are gone, and we get about 9 times 10 to the 9 newtons. That is 9 billion newtons. Now, to put that into perspective, the largest ship in the world is the TI-class supertanker, and the gravitational force on a fully loaded TI-class supertanker is about 5 times 10 to the 9 newtons. So a stack of 2 fully loaded TI-class supertankers would have a gravitational force on it that is about the same as the electrical force on 2 1 coulomb charges separated by a meter. What this tells you is that a coulomb is a huge unit of charge. If you ever meet a 1 coulomb charge, my advice is run. Now that we know how to find magnitudes of electric forces, let's talk more about direction. We know that opposite charges attract each other, and that like charges repel. That allows you to conclude that the electric force always acts along the line connecting the two charges. And so it would be nice to have a notation that allows us to easily write down vectors pointing in that direction. And so what we do is we define a unit vector that we would call r hat 1, 2, which is defined as a unit vector, a vector that is unitless and magnitude 1 and points in the direction from charge 1 to charge 2. This will be a convenient vector for writing down these electrical forces in fully vectorial form. So let's look at these two like charges repelling. you can see just from the diagram that we must be able to write the force that 1 exerts on 2 as the magnitude of the force that 1 exerts on 2 times the unit vector r hat 1, 2. It is in the direction of that r hat vector. And we know how to get that magnitude, F12. So, what about the force that 2 is exerting on 1? Well, we could now define the other unit vector pointing exactly the opposite way and write that force down in that way. So, we have 2 unit vectors, one pointing from charge 1 to charge 2 and the other pointing from charge 2 to charge 1, and we can write down each of the forces in terms of those unit vectors, and we know how to get their magnitudes. Similarly, if these charges have opposite sign, then the forces act the other way. They are attractive. And so now the force that 1 exerts on 2 is negative its magnitude times r12 hat, and similarly the force that 2 exerts on 1 is negative r21 hat. Just look at the vectors and you can convince yourself that these relations are correct. Well, that means there's an easier way for us to rewrite Coulomb's law to have the direction built into it. Notice that Q1, Q2 without absolute values would be positive if Q1 and Q2 are both positive, and it would also be positive if they're both negative. But it would be negative if they have opposite signs. And so we can just write the fully vectorial F12 as KQ1, Q2 with no absolute values over R12 squared times R hat 1, 2. If you're like most students, you're finding this notation a little bit intimidating. Don't worry, it's not as hard as it looks, and in the next video lecture I'll show in detail how you use this, and you'll see that it's actually pretty simple. I'll just finish up this video lecture by talking a little bit about when Coulomb's law applies. So first of all, it only applies to stationary charges. And so we talk about this as an electrostatic force. It is a force between static charges. Now, in fact, it's a good approximation as long as the relative speed of the charges is much less than the speed of light. However, as we'll see later on, when charges are moving quickly relative to each other, there are other forces that they exert on each other. The other thing that I mentioned at the very start of the video is that Coulomb's law only applies to point charges. Anything that isn't a point charge, in other words, charges that are spread out over some object, is what we call a charge distribution. With some difficult math, you can show that Coulomb's law also applies to forces between spherical charge distributions, where what I mean by that is charge distributions that are fully spherically symmetric. One thing that means is that if you have uniformly charged objects at fairly large distances from each other, where by large here we mean large compared to their own radii, then Coulomb's law will be approximately correct. However, especially if these objects are made of conducting material, as they come close to each other, they tend to polarize each other. This means that the charge distributions on them are no longer spherically symmetric, and so Coulomb's law is no longer correct for them because the distance between their centers is no longer the same as the distances between the centers of their charge distributions.